Dear mentors, in this video we'll discuss how to balance concepts and procedures when you teach mathematics. So there's two types of understanding in mathematics. One is conceptual understanding, which some people also call it relational understanding. And then there's procedural understanding, which also it's called instrumental understanding. So in this video, we want to answer the following 4 questions. What are their differences? What are the advantages of each? How and when to use them? And finally, probably the most important question, how can we balance them? How can we balance concepts and procedures? So first, it's important to understand what is what. So let me introduce Richard Schempp. So he wrote a paper called Relational Understanding and Instrumental Understanding, which in our terms should be conceptual understanding and procedural understanding, in 1976. And he had this beautiful analogy of a map. So he said, imagine you're new to a town or to a campus, any complex place in which you want to navigate, in which you want to move, get to other places. And so he said you could have 2 different mindsets to approach this. First, you could just use a little map that tells you how to get from place A to place B by following some routine, some steps. And you could do that. You could pretty much use your GPS, say, or follow some particular instructions, turn left once you get to the church, then walk this way, etc., etc. And that gets the job done, no doubt about it. But then he says, what if I change my plans? What if now I don't want to go to that place, but maybe to another place? Can I go back easily? Maybe there's no way to go back following the same directions. So another way that he proposes is, instead of looking at steps or prefix routes, just look at the relations that are in the map. Just get immersed into the map and understand it as a whole. Understand how this place connects to other places. And then when you get this type of understanding, it's going to be much easier to get to any place, to a different place. So this analogy serves us to capture these 2 types of understanding in mathematics. So first, conceptual understanding, which is relational, means knowing the meanings of mathematical objects and their connections. It's holistic and it's also flexible. It's very versatile, as we talk about in the map analogy, and it uses models to make sense of the mathematical world. And it also provides the reasoning behind procedural understanding, so that's going to be the connection. Now, procedural understanding or instrumental understanding, it's knowing the rules and the steps, the recipe, to find the answer to a given task or a problem, which may be narrow or maybe a little more open, but it's always specific. It's sequential and it's rigid, and it uses models and instruments for performing things. What it actually does is it provides systematization, so routines, and that enables deeper conceptual understanding. So what's important to know here is that actually both help each other, and that's nice, that's good. So what we want to do is understand that first. Conceptual and procedural understanding nurture each other. Both need to be promoted in teaching, and you have to develop them hand in hand. Think back of the map. Sometimes when you're new to this first new to this place, it may be good enough to know how to get from A to B. But maybe if you go out the next day and you take a little detour, you're going to struggle a little bit, but you're going to gain some more knowledge. So that's how this nurtures. The problem is the following. Unfortunately, teachers and books and the educational system in mathematics usually focuses much more in procedural understanding. And of course, I don't have numbers, but if you ask me, you could say it's maybe 80% in procedures and just 20%, and sometimes even more radical. An example is the following of an example of procedural understanding or a procedural exposition to a topic, such as average, you could read this text. The average of a collection of three numbers A, B, and C is defined as A plus B plus C, all divided by 3. So that's a rule. That's a step-by-step. To find the average of three numbers, you first add them, and then you divide this result by 3. So that's nothing wrong with that. The only problem is that if you just leave it like that and you don't complement it with conceptual understanding, students may forget it. And even if they don't, they're not going to be able to transfer this understanding to other contexts, solve real-world problems involving averages between three numbers, knowing that average means balancing things or representing numbers in the best possible way, in a sense, etc., etc. So it becomes very poor. What are some advantages of conceptual understanding, which is the thing that we want to promote in balance to procedural? So here are some advantages. First, it prepares students to novel mathematical tasks. When I have conceptual understanding, I can work with many different types of problems in which many conditions can change or relate different concepts, etc., etc. So it's much broader. Then it actually makes procedures easier to remember. I can learn the procedure. I can also learn the concept behind and why the procedure works. And that would actually make my life easier when I just have to apply a procedure, which is totally fine. It'll just make me easier for me. It also boosts intrinsic motivation, which means the motivation of learning, not because of a reward, but just because I like learning, because I find pleasure in it. And it limits the need for rewards and punishments. So research has shown that when students are exposed to conceptual understanding, you don't need much rewards or punishments. It also stimulates curiosity and desire to learn, so in connection to that. And finally, it actually helps make less mistakes when using procedural knowledge. So research has proven that when kids are equipped with not just procedures, but with the concepts behind, they actually tend to be much more efficient and make less mistakes. So I want to illustrate now an example of procedural and conceptual understanding in a very basic context or situation, which is adding or subtracting fractions. So for example, you could approach this problem 1/2 minus 1/3 in many different ways. So you could approach it. Let's explore two cases, one that is more procedural, and let's explore another which is more conceptual. And again, the message we're sending here is not that you have to make a choice, but rather that if this is like a diet, you have to, get food from all sources. So you want to have the procedures, but also the concepts. And you want to help them help each other. You want to make that they help each other. Procedurally, we could follow rules. For example, we could say that, okay, if you have 1/2 minus 1/3, look for a common denominator first. That's 6. And then multiply 1/2 top and bottom by 3 to get the 6. And do a similar action for the 1/3, which would be 2 and 2, to look for a common denominator. So I'm elaborating some steps. And that's 3/6 minus 2/6. And then the procedure is that if I have the same denominator, I can just add or subtract the numerators. That's another rule. That's another procedure. I can do it whether I know why it works or why it doesn't work, whether I have a mental picture if I don't. That's independent of that. And so I get my answer now, which is 1/6. So this would be one way. But again, the problem is that you may put this in a test, or you may ask a kid to do it this way, and they can perform well. Nothing wrong with that, but where's the understanding? If you're going to measure it, how are you going to measure it? So conceptually, there's many ways to do this. Here's one way. I want to do 1/2, and then I want to remove, after I have 1/2, I want to remove 1/3 of that quantity. So you could draw it in the following way. Let's first draw a rectangle that represents a full unit, or a unit, you should just say. So 1. So this is my full units. So I'm using area as an excuse to build conceptual understanding of fractions. And area is just one way. There's many different ways, of course. I want to start with 1/2. So I'm going to break this into 2 pieces of equal size. And there's conceptual understanding. These are actions that have some meaning. I have to know what fractions mean and what they represent to be able to understand this problem. So that's 1/2. So here is 1/2. This is what I start with. And then what I want to do is I want to remove 1/3. So remove 1/3 to that 1/2. So here's how you can do it. I already broke the full unit in 2 by using a vertical line. Why don't I use now a horizontal line to break the same full unit into 3? That also builds conceptual understanding, just understanding that you have to start with the same unit if you are to perform these operations. It wouldn't make sense for me to start with a bigger or smaller unit and break it into 3, because I cannot really then compare fraction, subtraction. So what I want to do is first, I want to understand that 1/3 represents one of these 3 horizontal bars. So I do another picture of the same unit just for me to understand what 1/3 means. So this is the meaning of 1/3, is this shaded region. And now what I can do is also break this unit into 2. That's the magic trick somehow. And I get at the understanding that 1/3 actually represents 2 pieces of this unit divided into 6 parts. So of course you can start to see the connection. In the procedural, you would see this as here, 2/6. That's where you see it. Which, by the way, is a great way. You can compare, you first do it with a procedure, then you do it conceptually, or vice versa, and you compare how you did it. And now the insight is that if we had these full units, then 1/2 meant 3 of these 6ths, and I'm removing 1/3, which is removing 2 of these. So let's draw a last picture in which I had 1/2 which were these 3 pieces, and then I am removing 1/3, which in my new language of 6ths is just 2 of these pieces. And so what I can do is remove 2. So what I'm making the following argument. These 2 pieces here on the top are the same as any 2 pieces really on my unit. So I could, for example, remove these 2, because these 2 areas are equal here. And so what I'm left with is, of course, just 1 piece. So let's isolate it here. this little piece here. And now I have to ask, what is this piece? And that's also conceptual understanding. Well, the unit is divided into 6 equal pieces, and I'm just taking one. So this is 1/6. And that's the final answer. There's other ways to do this. We could do it with bar models also. But I just wanted to illustrate how this blends. Don't be afraid and don't tag your explanations. This is just procedural. This is just conceptual. You want to mix them because kids should be exposed to both. So that's important. I'm not making a case that something is better than the other. It's not that simple. The case I'm making is let's really boost conceptual understanding because we really need it. Thank you.